Next, let's begin talking in particular about graphs. With the graphs of polynomials, as with other things that we've seen so far, all the key graphs, we want to achieve facility so that we can look at an equation and see a graph, and look at a graph and see an equation. So that's where we're going to start our discussion here. When we talk about the graphs of polynomials, I'm going to be talking about two things. First is the end behavior, which means what happens as x becomes infinitely large and positive, or x becomes infinitely large and negative. So the other thing is what I will call the interesting part. And this has to do with the zeros of the polynomial, as we'll see. Okay, so there's a particular kind of polynomial known as a power function. Example, y is equal to x cubed, or y is equal to x to the 10th, or in short, y is equal to x to the power n. Okay. Or some authors will say y is equal to a times x to the n. They'll allow a single real coefficient here. Okay. The fact is that the power functions, as long as we do not have what we would call some lower order terms out here, just the term that gives the polynomial its degree, these all look alike. So all of the even power functions look more or less like x squared. Which of course has a shape like this. And the important thing is, as long as there isn't a negative coefficient in front of it, it goes up on both the left and the right. All of the odd power functions look more or less like x to the third. They have this nice curve there at the origin. Now, all of these functions, x to the fourth, x to the 10th, x squared, go through the same points of 0, 0, 1, 1, negative 1, 1. All of the odd ones go through 0, 0, 1, 1, negative 1, negative 1. They all have these in common. And the shapes are a little bit different, as you can see if you look in Desmos or your calculator. X to the fourth, for example, is less than x squared between 0 and 1, and then greater than x squared for x with a magnitude greater than 1. But the nut of it is, it looks pretty much like x squared. Okay, and x to the fifth, similarly, is a little closer to the horizontal axis between x equals 0 and x equals 1, positive or negative, and then farther from the horizontal axis for other powers, but it still looks fundamentally like x to the third. Now, just in case we have a negative leading coefficient on our power function, so for instance y is equal to negative x squared, well, we know that that's a reflection over the horizontal axis, and y equals negative x to the third is also a reflection of x third over the horizontal axis. Okay. So I'll be talking about functions that start high and end high, or that start low and end low, or maybe start high and end low. It's all going to depend on whether the leading coefficient is negative or positive, and whether the degree of the function is odd or even. Keep that thought. So here's our first example in which we're going to look at both the end behavior and what I call the interesting part. This example is y is equal to x squared minus 2x minus 8. Okay, so first thing we see is it's a quadratic. We know that it's a parabola that is going to go up at both ends, and we know that because we're familiar with polynomials of degree 2 already. And now we need to consider what's happening between these two ends. That's what I call interesting. Well, we have several ways of looking at this already. We could use the quadratic formula on it. We could do the h equals negative b over 2a thing and so forth. We could do what I like best, which is to complete the square. X squared minus 2x plus 1 minus 8 minus 1, so x minus 1 squared minus 9. Or we could do something else. In particular, we could factor it. So I chose this because it's easy to factor into x minus 4 and x plus 2. Now, that's our y value. If we were looking for the zeros of this, we would say 0 is equal to x minus 4 times x plus 2, and we would know that y is equal to 0 when x is equal to negative 2 or x is equal to 4. So, continuing our graphing thing here. Okay. There's 1 0. There's another 0. I have my up arrows at the right because it's going to be a parabola. And another thing that I like about factoring is halfway exactly between the zeros is where I'm going to find the axis of symmetry. And we know from having completed the square up here that that axis of symmetry is x equals 1. So I'm going to come down here and put the point that we calculated previously, 1, negative 9. I hope I said that correctly a moment ago. Now I connect the dots. Okay, so factoring this polynomial, this quadratic, gave me these two zeros, and I already knew that it had to go up at the ends like this. And in this case, completing the square also gave me the vertex. But what we're mostly interested in with polynomials in pre-calculus is this. Where, that means for what values of x, is the function positive, negative, or 0. Okay. Well, okay, the zeros we have. Y is equal to 0 when x is equal to -2 or x is equal to 4. What about positive or greater than 0? Well, here is where y is greater than 0. What is x there? X is less than -2. Or here, y is greater than 0 and x is greater than 4. It's not equal to 4. We already said that if x is equal to 4, then what we have is a 0. So, next thing I'm going to write is y is greater than 0 when x is less than -2 or x is greater than 4. Notice these are open intervals. And so that leaves inside this space y is negative, less than 0, and by negative all I mean is it's below the horizontal axis. These y values are negative numbers. Okay, so y is less than 0 when x is in the interval -2 to 4. Okay, so just for grins, I have written my open intervals in different ways with this notation and with that notation. Either one is perfectly all right. Okay. Let's let that be the end of this portion of our program.